The topic of this lecture is electromagnetic induction. In prior lectures, you have learned that if you have a current flowing through a wire, it actually creates a magnetic field around that wire. And so people started wondering, is the opposite true? So if I have a magnetic field, can I actually create current from that? The answer is yes, and it was discovered independently by two experimental physicists, Joseph Henry, who's American, who actually is a native of Albany, and Michael Faraday in England. So Joseph Henry is often not as well known as Michael Faraday. So he lived at the end of the 1700s into the 1800s. He was really the premier American scientist after Ben Franklin at that time. And as I already mentioned, he was a native of Albany, New York. So he attended and actually taught at the Albany Academy, which is a school that's still in existence right now. And he was a full-time teacher there and conducted experiments in his spare time. And that's where he was actually started experimenting with electricity and magnetism. So other cool things, he was invited then to Princeton once he became a little more established. There are still the Joseph Henry laboratories there. First secretary of the Smithsonian and one of the first members of the National Academy of Science. So here's the basic things you need to know about induction. So current is induced in a coil when there's an external magnetic field, and that magnetic field has to be changing. So the picture here is showing you a battery that's looped up with I'll get my pointer going. So our battery is connected to some coils of wire, and then more coils of wire are connected on the other side to a galvanometer, which is just a very sensitive instrument for measuring current. So Faraday discovered that if he closed the switch or opened it, there was a current induced in this side. And maybe Dr. Hassel actually would set up a little demonstration so you guys can see this. So the key is that the changing magnetic field on this side, right? So if we have a current that starts and stops, we know magnetic field is created in these wires. The field is felt over here, and when it changes through these loops, you get an induced current. So here's a simple experiment. Again, if we were in class together, we would do this so you could see it. And again, this is a galvanometer. You just have a loop of wire here, maybe even a bunch of coils of wire, and a bar magnet, and that's it. And so when this deflects from zero, either plus or minus, it's telling you that current is running through the loop one way or the other. So here, in the first case, you're moving a magnet up toward the coil, right? The north side's going up, and you see that the galvanometer is deflected to the plus side. Okay. Then if you pull it back out, it gets deflected to the other side. And then finally, if I just keep the magnet still and I'm not moving it at all, I get no current. Okay. So as we saw in the last slide, if I move the magnet in, I got current in one direction. If I pulled it out, I got current in the other direction. And so how do we actually figure out what that direction is? So we know now that there's a changing magnetic field through wire loops induces a current, and now we can try and figure out what the direction of that current is. So Lenz's law is the principle that helps us figure out the direction. And the idea is basically that the current that's induced is trying to resist any change in the magnetic field that that loop of wire is experiencing. And so probably the best way to show you is just one example right now. So we're going to look at this, right? So the example is, imagine that a wire loop is sitting in a magnetic field that's directed into the page, and then the magnetic field is then switched off. So let's see what that looks like. So we have our wire loop, and it's sitting in a field that's going into the page. Okay, so that's the first part. And then there's a change. So whenever I solve these problems, I set it up as a before, right? What did the system look like before? What does it look like after? And then that helps you figure out which way the induced current will be directed. Okay, so this is what it looks like after. I just have my wire loop and suddenly the field is shut off. Okay, so I know that this loop wants to get back to its original state, which is having field lines into the page, right? So it wants to look something like this again. And the current that's induced will be such that it creates a magnetic field into the page inside the loop, okay, to try and get it back to where it was. So if we use our right-hand rule, if we want a field going down into the page inside the loop, I need to have a clockwise current. And the current would be induced in that direction. Okay.